stuff. Yeah, essentially it looks something like this. Imagine that you have a bunch of line segments on the x-axis. That's what's sitting over here. And imagine that you're given points somewhere on top. Your job is to connect the points to somewhere on this line segment using as short a link as possible. So in this case, if you think of this triangle, what do you think is the shortest line segment that connects this point to somewhere on this segment? It's going to be a horizontal drop, right? It's going to be a perpendicular drop. Over here, it might be just that line segment. If this point is a little bit off, it may be just the nearest point. So things like that. Okay. The only problem is that depending on where these points sit, some of these line segments might end up intersect, and you are not allowed to do that. Okay. If they intersect, you have to move them in such a way that they don't intersect and still make sure that the total length is minimized. And it's also possible that you just cannot do it, and then your job is to report that this is not possible. Okay, so what I said here was there are some easy cases and not so easy cases. This is the easy case when the point is directly above the line segment, and then all you have to do is a perpendicular drop. You already know that. If the point is a little bit off, then it's going to be the closer of the two endpoints of this line segment that you have to connect. But this is if there is no interference. If there is interference, then things go crazy. So that's the much harder case. And if none of these things intersect, then life is easy, and you can go and connect them, and it's quite easy. But if they start to intersect, then things get messy. So for instance, if there is a line segment here and the corresponding point is there, if there's another line segment here and the corresponding point is there, I can't just pick the shortest line segment and connect them because they will end up intersecting. So question is, what do I do then?
Shift it.
Shift what?
The vertical line.
So the vertical line has to be shifted in what way?
To the right.
So it needs to now be slanting and needs to pass this particular point here, right? So how do we know that's the best? How do we know that's the optimal connection? Is it possible for me to move this guy somehow and improve things? And just by staring at it, you kind of can convince yourself that you can do nothing with this side. You really have to fix this line segment so that it clears this point here. Now, our goal is to formalize this into a algorithm and then turn it into a computer program. And we need to make this efficient because we have to make it efficient because why?
We're engineers. That's how it is.
That's what was requested.
Well, not because it's our mission in life, but because there could be up to 100,000 points. Okay. And what does it mean to be efficient? Well, because there are 100,000 points, that's 10 to the 5. If we write an n squared type algorithm, are you guys familiar with what n and n squared and so on are? If you have an n squared algorithm, it's going to take 10 to the 10 different calculations. And 10 to the 10 is just way too large. Okay, there's no way you're going to get that done in any reasonable amount of time. So therefore, any kind of n squared algorithm is a no-no, all right? And so our job is to kind of figure this out. Now, the time complexity adds a little extra challenge to this problem, difficulty to this problem, but let's first make sure we understand how to solve it, then we'll worry about the challenge of time complexity, of efficiency. All right, so the other thing that we need to understand is, when is there no possible solution? Is that something, can we even come up with a simple example where it's not going to happen?
if the endpoint surpasses
Uh-huh.
if the top, I don't know what it's called, if it's the endpoint, but.
You mean to say, if I drag this out somewhere here?
Yes, right. If you drag it outside of
Yeah.
that line.
But how do I articulate that? How do I test for it? What is that something
The-
that you can explain?
If the X value of the,
Well, it doesn't even have to cross this X value, it could even be here, then it still would be
that's
difficult.
true.
You're gonna say something. Hold on a second, let me get, because you were here last time, right? Yeah, let me get hear from him and then I'll
But
come.
if you like, or sorry, if the more slanted one was pushed further, wouldn't you swap the roles? Meaning the top point would connect to the left side and the rightmost would connect to the bottom.
What we're saying is that, well, I can actually draw it here.
Yes. Sorry about that.
So, here's one triangle, right? Oh, what's that?
It's asking to copy.
Okay. Here's one triangle,
Yes.
and if nothing challenges you, I would do that. But now I have, so here, this was your line segment, right? What if I take another one somewhere here? All right? And throw the point for this somewhere here. Oh, come on, what is that?
Oh, the points are linked to their disjointed. You can't swap them.
You can't swap.
Ah, okay, that makes very.
So
They're paired.
if
they're-
they intersect-
They're paired to, for life.
And then yeah.
So if they intersect, the other
Intersect
triangle.
what? Intersect what? Is that clear to you?
I think it's that, for any pair of triangles, if one leg, or if each of the legs
Mhm.
of, one triangle intersects both of the legs of the other, then it's not possible.
If each of the legs of one triangle intersects at least one leg?
Both of the other
At
triangles,
least-
then it's not
So
possible.
both legs should, so you're saying both, the two sides of the triangles, because the third side is anyway on the x-axis, it's not relevant. The two other sides should intersect, that's what you're saying.
I'm saying that they can't intersect twice, like, in that example that you drew there,
Yeah.
like, if
Okay.
you consider the left. triangle-
My question is that enough? Is that test enough? Because that I could, let's just say, let's not worry about the n squared thing. I could go and check for every point whether this happens, right? Theoretically. Is that enough?
It might not be sufficient.
Other possible challenges here. You were gonna say something, I'm sorry I stopped you.
No, I just got myself, because I was gonna say something about it being before, but then I created a situation where it did not work in my role, and I was like, okay.
All right, fair enough, yeah. So I know there's some important information you can.
Yeah, you can.
Okay.
The fifth option. And then just draw a line through all the words.
You can just do the one to the right of it, it clears the entire screen.
Oh, but then I lose
Oh.
that also. Okay, fine, I'll retry.
Yeah.
Okay, you lost that, it's in your head,
Sorry
but
about that.
what do I do now? So, listen, so the question we are asking is, what are impossible situations? Is that something that you could articulate?
His idea was the.
Well, I
points
understand
crossing.
that, so that's one case and we already drew it.
Yeah.
Are there other cases, are there other scenarios where that doesn't quite happen, but still I can't quite draw it?
What were the questions are?
Oh, if
What are impossible situations?
if 2 points are, I don't know what the best way to say it, but behind one another. Like, I'm thinking about
Uh-huh.
But it's not just that they're behind, it's behind and they're too short according to the length of the segment. But the thing, how do I find out the
I-
ratio,
it's
because I can
easier if I
calculate
just-
that.
So,
It's like.
So you have the.
so here's my x-axis.
Yes.
Okay, and then,
The 2 line segments.
You wanna draw two, alright.
Yeah.
Let's do that then. So here's one. And here's another.
And then let's say both points for the left and the right
Yeah.
are inside or on top of the right line segment. So place one just
Top of
anywhere.
the right line.
Yeah, just place
Okay,
one
so
anywhere
you wanna
there.
draw one point here. So yeah, okay, so you wanna draw one here and one here, that's what you're saying.
No, the bottom one, yes, but the right one has to be like
You wanna-
in the
But-
way.
But that's the same as the earlier case, so that's already accounted for. Let's say I can test that.
Yeah.
Are there other nasty, impossible situations, right? That's what we're asking. Could I draw one with 3?
Oh, can there be multiple points per segment? Like,
Sorry?
can you have like, let's say 3 points and then one's,
No,
So one
but there
point.
could be 3 pairs.
The x-axis segments can't overlap.
No, they cannot. What if I have, this guy, right? Okay. What if this guy were like so? And what if there was another one over there? And let's say that one goes like so.
Ah.
And that one looks like that. Possible?
Very.
Yeah?
Yeah, the middle one wouldn't be able to
wouldn't that be too,
touch the x-axis.
Would that be,
like your, it's 2 lines per 1 point?
no, everything is legal here. I got 3 line segments, they're distinct.
Oh, I see you're drawing the triangle.
And my 3 points are 1, 2, and 3. I need to erase that one there. Come on, go away, oh, no, good. Alright, yes, Jan?
And just to be sure, we're still like disregarding like any efficient solution, like we don't have to.
Yeah, let's put aside efficiency for a bit.
So then you don't have to consider, just a pair of 2 points.
Okay.
If for any specific triangle, if both legs if each leg intersects 2 legs of any other triangle, then it's not possible.
That doesn't look enough. What if I shorten this to just go there? You think now it's not possible?
I don't see how it's possible.
Why not?
I may be wrong.
And I shorten this also to just touch this and come back. You're saying it's not possible?
Well, in that case, it would be possible, cause it
Yeah,
doesn't.
so, but then your, the condition you just stated is not enough, right?
When I was referring to intersection, I meant like strict intersection, not at the endpoints.
Well, okay, I can, come on.
Yes.
Alright. Okay. I will now show you how this could happen. Alright, this is my first one. Okay, now I'm going to do strict. Does that look strict enough for you? Does that look strict enough for you?
If the x value of the points overlap each other,
Uh-huh.
then there isn't a straight line for the third segment to connect to the x-axis.
Well, Here there is, right?
No, yeah, but they're not overlapping each other. The X value of the.
Yeah, but
the
in
other
the
two
previous
segments.
example, they were not overlapping each other, so I could have done, what I told you was, this could be like so.
Right,
And this could be like so.
there you go.
They're not touching, these two are not touching each other.
Oh, but the X value is.
Yeah, but, that's not enough, because it could be like so. The X values is not
overlapping,
helping you now.
So it's gotta
right?
be more than just that condition.
Yeah, so it is getting nasty,
Yeah,
right?
It has to be for both.
Yeah, but.
Otherwise.
Well, you know, I can make it.
Are all the numbers that you get for the segments gonna be like,
Disjoint,
like
yes.
one, like from 1, 2, 3, like no, like 0 point fun?
Yeah, it's integers, yeah.
Like integers, so like.
Yeah, it is integer. All integer values, yeah.
so if they overlap within a third segment.
They could overlap, and yet maybe something is possible. Sometimes it may be possible and sometimes it's not. So it's not enough just to look at the line segments. This is what I'm trying to get at, okay? Is that clear for everyone? Okay. All right, so let's now start to look at more details. Any comments or questions? Everyone okay so far? Yeah, okay. So, essentially the idea is that we're going to not worry about whether the ends of the triangle intersect and blah blah blah. Instead, we're going to focus on whether any point can see the x-axis.
Which makes sense.
Sorry?
No.
Makes sense, right? So now we have to make this more precise and then turn it into something that can be coded, right? So let's move further, see what else we can say. Now this is this is the example I just showed you. So there are all sorts of cases that are possible. So here's an approach that's going to help you. Because this is not an easy problem, I'm jumping ahead and trying to give you more details of how this solution is going to get worked out. Okay. So let me erase this here. Everyone okay with me erasing this? Clear. Okay. So let's say that we are. Remember, we have an x-axis. And remember that we are given these bunch of line segments on the x-axis. So here's one, here's the second one, here's the third one, here's the fourth one, and so on. These are your line segments that are given to you. And you're also given paired points about this. This is your situation. This is your current. So there are going to be points here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I don't know which one is for which, but you're told exactly which one these are. This could be number 1, this could be number 2, this could be 3, this could be 4, and this could be 5. You'll be given points like this, and your job is to figure out, first of all, whether it's even possible to make non-intersecting line segments, and if so, you want the shortest one possible. All right. So what we're going to do is, remember, these line segments are also numbered 1, 2, 3, 4, 5. Fine. And these are pairs, so 1 has to be paired with 1, 2 has to be paired with 2. You don't have a choice. In this particular case, it's kind of clear to you that you're never going to be able to do it just even with 1 and 2. It's not going to work out because they're intersecting. Is that clear? So so here the answer would almost easily be no. So let's fix this and go with it, the doable case. Let's move our 1 somewhere else. So let's say we move our 1 somewhere here. Okay? Now this is 1. And now it may be possible, right? So the question now is, can 1 see the x-axis? And then we're going to ask if 2 can see the x-axis. Well, if I don't draw any line segments, everything can see the x-axis. There's nothing surprising there. So really, what does it mean to say see the x-axis? So here's what we're going to do. We're going to process our line segments, our pairs from left to right. And as we process them from left to right, we're going to do some processing. Sorry? Yeah, you've heard this before. So, so the way this works is, I'm going to look at the ith point. In this case, let's say we are looking at this guy. Okay, let's say we process 1 and 2. Things are okay. We've judged that things are going well so far. Our question is, can I do 3, and can I do it? Once I know I can do it, I'll go and find the shortest one. So the way I'm going to do it is as follows. In order to get 3, I have to make sure that, well, it connects somewhere. So this is my triangle. Somewhere my line segment is going to be within those 2 rays, right? What I'm going to see is, where are all the other points? In order to figure out the other points, I look at all the points to the left of this, and I'll create what's called as a convex hull of these points. Now, what is a convex hull? By the way, I need to put in more points here. It's not enough. 5 is not enough, it seems. So I'm going to have to fix this a little bit, so please forgive me. Let's assume that there are a lot more pairs. Yeah.
Oh, Dr. Giri, when you say left, you mean like you're also considering all the points that are on the same like vertical axis? That
No, no. I'll explain that in a second. Give me a couple of minutes. So remember, I have line segments that are numbered 1 through n. Okay. So I have up to n line segments. Now, what I'm going to do is I'm going to find this guy's pairing point and see if I can connect this. Once I know I can connect it, I'll find the shortest one. And the question is, what is the consideration for each one of these? So let's say I'm going to look at the ith point. So this is the this is the ith point. So we're somewhere in our processing. We've processed all the points to the left. We haven't processed anything to the right. We're looking at the ith point. So this is the point of interest, and let me just color it differently so that you understand what we're looking at. All right. Okay. Now the question is and let's also assume that this guy's paired line segment is this one here. So let's say this is the ith line segment. Yeah.
The iteration is from the line segments left to right?
Yeah.
Okay.
Yeah. And so the question is, am I going to be able to connect that point with this line segment without having trouble? And so the way I'm going to do this is as follows. I'm going to look at all the points 1 through I minus 1. Some of these points may be over on the right side, some of them may be over on the left side, we have no idea, right? But what I'm going to do is I'm going to take all the points to the left and I'm going to build something called the convex hull. By the way, the convex hull is as follows. If these are my points, the convex hull is essentially a polygon that encloses all the points, which means in this case, it's going to look like this. It's going to look like this. It's going to look like that. It's going to look like that. sorry, bad line there. That's the convex hull. So essentially it's the polygonal boundary that encloses all the points. Is that clear? Now what we're going to do is to take all the points 1 through I minus 1, and we're going to build a convex hull of this. So let's assume that my points 1 through I minus 1, I build a convex hull exactly like that, and let's say it gives me this as my convex hull. Remember, the points for the 1 through I minus 1 could be anywhere. It could be to the left, it could be to the right of that point, it doesn't matter. Fine? Then I'm going to take all the points I plus 1 through n over on this side, and I'm going to build another convex hull for it. Okay? And I don't know, in this case, let's say that it looks like this. All right? So essentially I've taken all the points that should have been to the left and all that should have been to the right. And now I'm going to ask the question, think of these objects as obstacles. Okay? So think of these as concrete blocks. Now, if I stand here, can I see my x-axis? In particular, can I see the paired line segment? And in this case, the answer, of course, is yes, because I can now see my x-axis, which is somewhere there, but then I can't quite see the other end of it, right? The other end is somewhat obscured by this concrete block here, so the other end really is going to be somewhere there. It's going to cut through that point and will only reach there. So I can see only this portion of the line segment. And now my job is, if I can see this much of the line segment, I'll pick the shortest line segment. And this is never going to get obstructed by any other choices you make. Does that make sense?
Mm-hmm.
So this is the general strategy for solving the problem. Yeah.
I think I might have come up with an alternate solution, but it's physics. But I don't know.
Can you give me a few minutes to
Of course.
flesh out my solution, and then I listen to you? Yeah.
How do we know that? Because
How do
in
we
this,
know
in
what?
this, in this
Yeah.
algorithm or this
Yeah.
idea, you're avoiding the points, the convex hull.
Right.
But in the original problem, you want to avoid the lines that they create with
Good.
the.
Perfect. So the answer is the following. First of all, anything here is going to connect to a line segment that's beyond here.
Okay. Yeah. Agreed.
Okay? So therefore, if you're starting from outside of this triangle and you're going somewhere that's further out on the x-axis,
It's fine.
you're never going to intersect.
Mhm.
Same argument on this side. Now, you have, the question you're asking is this enough?
Mhm.
Okay? Can there be a shorter one? And the point is that whatever line segment you draw, okay? Let's say in the end you say, my best line segment that I'm going to use is this one here. Okay? Whatever that line segment might be, what we do know is that there is a line segment for I plus 1 to connect to its point.
Mhm.
And that line segment starts to the right of this. And because it doesn't intersect it, it's going to bypass that line. And so therefore, if I'm going to bypass that point, I also bypass that convex hull. And so I'm going to be fine.
I see.
Does that make sense?
Yeah. And if the point is inside the convex hull, it's still in bad.
If it's inside the convex hull, it's still part of the convex block, and somewhere you're not going to be able to see through it.
Yeah. Okay. Makes sense.
So you would iterate this process of building two convex
Ah,
hulls?
good question. So I encourage you to think about that. Give me a minute so that everyone absorbs this, and I'll get there. But is this becoming clear?
The convex hulls are created based off the left and right side of I.
Correct.
Okay, so I can have
Correct.
like a 5 on the left side.
Sorry?
Assuming this I is like number 4, I wouldn't have the 5 point on the left side.
That's right, it'll never happen, because the 5 will be in its convex hull on the right side, right? Yeah,
And going back to my earlier question about dealing with points that are on the same vertical axis as the
Yeah.
guide point,
yeah.
how would you consider those, would they be like considered as being left or right?
Well, it doesn't matter, so what'll happen is, you will have, 2 points like this, okay? One of these must be, each one is paired to a line segment. One of its pairs must come before, so you would have processed it. So this guy here, let's say is going to the left side, so this would be part of a left convex hull. All right, there'll be a right convex hull. If it messes up somewhere here, then this guy will never be able to see the x-axis, right? If it doesn't obstruct the right-hand side, then you have somewhere here, you have a way of going through, and you'll see that sliver for the x-axis. And then you can intersect this with the appropriate paired line segment, and you'll know exactly whether the line segment can be seen or not. Remember, it's also possible that the line segment for this guy actually is somewhere over here, right? It's possible. So even though you can see the x-axis, you can't see the part of the x-axis that you really want. Or it could even be on this side, same problem. But if you're seeing any part of it, right, then all I have to do is to pick the best one, the best line segment to whatever part you can see. So you intersect this pink line segment with the part of the x-axis that you can see here, and you'll be done. Does that make sense?
So just to recap, you're proposing that for any other points on the same vertical axis, you can just arbitrarily throw those points into one hole or the other?
No, every point is properly labeled right at the start. It's not like I'm sorting it. I'm only sorting the segments, not the points. Once I sort the segments, the corresponding points are numbered. They're given to you already. All right? You have no choice on how you're going to number the points.
Oh, okay, so you're saying that the left hole is points 1 through
1 through I minus 1,
and then
the
the
right
right
is
is
I plus 1 through n.
Okay.
Exactly. Yeah.
And the x-axis would have to be a subset of that, of the x-axis of those 2 support vectors for each convex hull.
You
That's
mean
what I'm
the
saying.
2 sides of the triangle?
Mm-hmm, yeah.
Well, that's how the problem is framed, so yes, sure. Did you have a question? So this is the general idea. Now there are lots of little details to take care of, but if you understood this, you made a lot of progress. Did this make sense? Yeah? Okay. Now the question is, convex hull and whether I can see the x-axis and intersections and blah, blah, blah. There's a lot of detail here. So this is not an easy problem, but I want you to understand this sort of high-level algorithm that you can slowly dig into and eventually understand all the pieces as much as you need. So let me show you what I have on the slides. Are there any other questions before I move on? So first is we need to understand convex hulls. If I have a bunch of points that you see on the left-hand side, then the convex hull is that. Very, very simple. Convex hull is simply a set of lines. So one of the ways to define the convex hull is that if you take any of the sides of the convex hull, if you extend this to infinity, right, then all the points will lie on one side of the line. So if I take this side here, or if I take this side here, it can be, and I extend it to infinity, everything lies on one side. Okay. That's what a convex hull is. So for these set of points, this is the convex hull. And you can connect it to the thing that I drew over there. All right. Now it turns out that there are algorithms in the textbook that will take endpoints and build a convex hull in n log n time. Okay. So let me write that down here somewhere so that we don't forget. Convex, oh, no, I don't want that. Let me also erase this here. Alright. Convex hull of endpoints can be done in n log n time. So therefore, for any point I can do the left side convex hull in n log n time and the right side convex hull in n log n time. So at least the ith iteration looks manageable so far. Is that clear? Okay. Now, the thing that I have to figure out is what part of the x-axis can I see? Which means I have to know where I'm going to hit the edge of the concrete block, right? So how do I do that? Well, it turns out that for this, I have to use something called the tangent problem. If I have a point here and some convex polygon, these are my two tangents. You guys are familiar with tangents. Now, so for this particular tangent, this particular polygon, and from this point, there are, in fact, from any point outside, you will have two tangents. By the way, if the point is inside, no tangents. You cannot build a tangent from inside the polygon. Okay? You have to be outside in order to build the polygon. In order to build the tangent. But if you're outside, you will always have two tangents. Clear? Okay. Now, in order to find those two tangents, it turns out that you can use something like binary search in order to figure this out. And this is a little more complicated. At this point, I'm not even going to try to explain this to you, but I can find these tangents in log n time. And that's what you need to know. Okay, so I can find tangents in log n time. I can find one tangent in log n time, and I can find both tangents in log n time, 2 log n time, and since I have two polygons, one on the left and one on the right, I will do this 4 times, and I'll have four different tangents. Now, out of these 4 tangents, only 2 are relevant. Remember, from this point, let me erase some things here so that there's some clarity. It's okay. So I don't know where this point was, but let's just say it was here. This was the ith point, right? I will draw 2 tangents from here. One will go like that, and one will go like that. Fine. And I will draw 2 tangents to this side. One will go like that, and the other will go like that. Fine. And now, only 2 of these tangents are relevant. I have to take this tangent for the one on the left, and this tangent for the one on the right. How you figure out which are the 2 relevant tangents is a little bit of work, but we'll worry about that later. So we know that this tangent doesn't have to be worried about, and this tangent doesn't have to be worried about. Fine? So we're interested in these 2 tangents. We also have to decide whether this tangent is clockwise of this, if this tangent were over there, then what will happen?
You can see.
You cannot see the x-axis, right? So just by looking at these four tangents, you can eliminate two of them, and you can figure out whether you can see the x-axis. All right. So that's the value of all these tangents, and pretty much you can do all of that in log n. How you exactly do that is you'll need a lot more geometry before you get there. For now, let's just assume that we know how to do this. Yeah.
What are these two tangents called? Because you can't just say left tangent, right tangent. There's no.
Yeah, it's a little tricky there. So right. Right. So the way you do this is, if this is your polygon, your point could be anywhere. It could be here, it could be here, you know, you just don't know. But you'll get two tangents. Now, those two tangents, first of all, you can see whether the tangents are going to hit the x-axis. If they're not going to hit the x-axis, you couldn't care less about it.
Agreed.
They're not going to ruin your life at all. Is that true? Yeah, they're not going to ruin your life because these are going off to infinity somewhere, right? So if they hit the x-axis, then you will know which one is clockwise of which, right? Because you can look at the x-intercept and figure out which one is relevant. In this case, that one didn't even hit the x-axis, so I'm never going to care about it.
I see. Okay.
So in fact, those two are easy. But if this polygon had been sitting like so, then you might get the second one over there. And then you know that one is not relevant, this one is. Okay? And finding the x-intercept is easy. If you want, we can talk about that. Yeah? Any questions about this? Is this somewhat making sense? Or is this a bit too much for?
If the left tangent, the
Yeah.
left relevant tangent was on the right side, that means the two
Correct,
points are
then
crossed.
yeah,
so you can't see.
then you're not gonna be able to see each other. So it's possible that this is your point, that one polygon sits like this and the other polygon sits like that. What's gonna happen? You'll find that this guy's left tangent goes like that, and this guy's right tangent goes like that, and now you've got things crossed. And so you're never gonna see your x-axis, which means forget it. Well, it is possible that your paired line segment is somewhere here, and so you may be able to see it. Okay, so you do have to, sometimes you have to worry about that other tangent. This is why you have to see whether the tangent hits the x-axis or not. Fine. All right. So now, what else is left? Finding the x-intercept. So, by the way, in the tangent, what I'm really going to find is not the tangent, but the tangent points. I'm going to find tangent points, which means that I'm going to find this point here, and I'm going to find this point here. Okay, that point I'm going to ignore because that tangent was not interesting to me. That point I'm going to ignore because it was not interesting to me. These are my two relevant points, and of course this guy here because that's the point I. And now I have everything that I need to solve the problem. So the first thing I'm going to do is I'm going to ask for this particular tangent, where does it hit the x-axis? Do you know how to solve this?
Where does the tangent hit the x-axis?
Yeah, so I have this point, I have this point. This is the point where the tangent started. This is the tangent point where it just touches the polygon, right? I want to know where it hits on the x-axis. Can I find this point?
With
Yes.
y equals 0?
Sorry?
Where
That's
do-
when y equals 0. So I could, since I have 2 points, I can figure out the equation of the line. Once I have the equation of the line, I set y equals 0 and I'm done. Clear? So finding the x-intercept is trivial. So I can find the x-intercepts of tangents. Again, easy. In fact, I can do this in constant time. Fine. Once I find the intercepts, I know exactly how much of the x-axis I can see. If they're crossed, I will know that I cannot see the x-axis, right? If it is not crossed, then I will know what section of the x-axis is visible. Then I'm going to intersect it with its paired line segment. Clear? And then once I have that, I will have another intersected line segment. Then all I have to do is to find the shortest one. That's easy. Okay, so that's how you do this for the ith guy, and then you do this for the next one and the next one and the next one. Now, if I do it in the way that I just described to you, I have to do this iteration n times. That means I'm going to have n times 1, which is order n times log n, which is n log n. All this is fine, but this one is a problem. Convex hull repeated n times is going to destroy you because that will become n squared log n. Clear? So I have to use one more trick in order to fix that problem. Okay. Questions at this point?
This is recorded, right?
Why, you were not paying attention? Yeah, you had a question. You were going to tell me another idea.
No, because I just realized, you mentioned the run time, it's like, no matter what, this is always gonna be the shortest run time, it's,
Okay.
but I can explain after, but.
Once you find the x-intercept, just making sure that the disjointed line segment is in between those points makes it okay. Like there's a,
Anything that's visible
yeah.
is never going to be obstructed by anybody. Because all the points here, they're going to join things beyond that. Anything over here is going to join points on this side. Well, even if they do, well, after I've intersected, so let's say that I do the intersection, and let's say that this is the relevant part of the intersection. I know for sure that anything I connect from here to here will never be obstructed by anybody else. And that's all that matters. Okay? You were going to ask a question?
No.
So really the only thing that's left is how do I solve the problem of doing n convex hulls, right? Everything else is pretty straightforward. Essentially I have to do this test at every point and to make sure that something is possible, and not only that, to figure out what's the shortest line segment that's relevant for me. In order to do the convex hull, I have to do one more trick. Let me see what this slide has. Yeah. But this pretty much describes what I just said. I'm going to find the convex hull of the left points. I'm going to find the convex hull of the right points. I'm going to find the tangents. I'm going to intersect it with the visible x-axis region, and I'm going to intersect it with its corresponding segment. Wherever that is, I'll find the shortest segment to connect it there. Yeah. Yeah, there's also pseudocode here. If you want to look at it, there's more detail than you'll ever need to know. So the only thing left is, what do I do with the convex hulls? If you guys are done with this, I'm going to erase this board. Okay. So we're now going to talk about a different problem that says the following. I have a bunch of points.
Oh,
All right.
Is this a new problem?
Sorry?
Is this a new problem? Is
give me a few minutes. You'll see that it is a different problem, but it's really not. Okay? Now, what does the convex hull for this look like? You already know this. It's going to look like that because that'll make sure everything is on this side. Then I've got that, I got that, I got that, that, and that, that. That's my convex hull. Fine? Now, I'm going to ask the question, if I gave you one more point, what does the convex hull look like? How does the convex hull change?
It depends if it's outside or inside of the.
Very good. So let's take the easy case. Which is the easy case?
Inside.
Then it's inside. So if the point is inside,
Doesn't change.
it doesn't change the convex hull. Great. All right. So then let me say if my point is here. So clearly I have to now modify the convex hull, but how do I do this? And so it turns out that, well, what do I use? What do I do?
Tangents.
Tangents, that's right. So I'm going to draw tangents from here. And here's the first tangent, right? The second tangent is, I don't know, my drawing may be horrible, but I think it looks like that. Yeah? How's that? You believe me? So it gives you two tangent points. So what's the new convex hull?
That space in between.
Sorry?
The space above the convex hull. Yeah, that adds to it.
Well, so, but what is the boundary of the convex hull? That's what we need to figure out.
From the intersecting tangent points to the new
That's right.
point outside the convex.
Yeah, so it turns out that it will have all this from before. Okay? And it will have the green portion from the new stuff, from the two tangents. And so two more edges corresponds to the two tangent lines. Everyone okay with this? So, I know I can find the tangents in
Log n.
log n time. So therefore, I can update this convex hull in log n time.
Log n.
Is that clear?
Mm,
So therefore, if I already have a convex hull, in order to add one extra point, I can do this in log n time. And this trick is enough to now crack open the problem, okay? So let me explain how it essentially solves the problem in n log n time. Here's the pseudocode. Maybe you don't want to see this pseudocode, it's too much for you for now. Let's go back here. Remember, we want the convex hull of points 1 through I minus 1. We want the convex hull of points I plus 1 through n. Now, in the previous iteration, we had already computed the convex hull of 1 through I minus 2. Right? So therefore, if we already had the convex hull of 1 through I minus 2, and all we had to do is to add one extra point of I minus 1, we just realized we can do this in log n time. Is that clear? So therefore, this step here, even though I told you it might take you n log n time, I don't need all that time because I can update it from the previous convex hull in log n time.
Got it.
Oh.
Right?
So instead of creating the convex hull every time for every point,
I'll
you
just-
already have the
I
point
already
before.
had part of it created, so I'll just reuse it.
Ah, okay.
Isn't a single update up to of n, but summed up over everything? Because you
No.
have to remove
No.
points.
Well, removal is easy because I'm gonna store it as a linked list. I'm not gonna store it as an array.
I see. I see what you mean.
So yeah, there are a few tricks that are needed.
But
for-
even if you use a list, wouldn't it not matter? Because you only remove a point at most once at the end.
That also is true, yeah. That also is true. Yeah, anyway, once it leaves, it never comes back.
Yeah.
Yeah. So, what we figured out is that this guy here, in each iteration can be done in log n time. By the way, over here, the right side is keep shrinking. Now, that's the reverse of this problem. And it's not as trivial as it looks. So this time you have to come at it from the other direction. Actually, I'm going to skip that part because it'll just confuse you way too much. But it turns out that removing points are a little trickier. But if you went and created all the convex hull from the right end, and now if you were to remove points, it's a lot easier. Because some of those old parts of the linked list are still there. All you have to do is to hook it back up. So with some little extra work, you can recreate the convex hulls on the way back. All right. So lots of challenges here. I'm not denying that it's a hard problem, but very, very doable. Ulysses is laughing. Look at it this way. This was the hardest problem in the competition. What I'm trying to do is to demystify all the pieces, to convince you that each of the pieces by themselves is nothing incredible about them. Okay? That's what I'm trying to do. I'm not trying to say that, yeah, you can go and code this up in a couple of hours. No, I'm not saying that at all. I'm just saying that the pieces are conceptually manageable.
One byte at a time.
One byte at a time. So if you were to build all those pieces and save them, all you have to do is to take it and code them up, right? So that's what I'm trying to convince you. I'm not trying to convince you that you can solve this problem easily. Questions? Did that make sense? Sort of?
Yeah.
You lost me somewhere?
Like you're really looking saying how to shrink the other convex hull.
That's not clear to you? Okay. All right. So let's talk about the shrinking part. So in order to understand the shrinking part, you have to understand the growing part. Okay. So the way the growing part happens is as follows. I'm going to store the pink convex hull as a linked list. You're familiar with linked lists and circular linked lists, right?
I'm actually not familiar with the data structure, so.
Well, okay, ignore that. Just forget about it. As he pointed out, even with arrays, it'll work out just fine. So I'm going to store the pink chain in an array. Now, this part of the array is going to go away. And it's going to be replaced by the green part, right? That's my new convex hull. The thing is that even though I'm removing this red part, I'm going to keep it aside and say, oh yeah, this I'm going to need later on in the ith step. Okay? And then I'm going to continue. In each step, I'm going to take the piece that got deleted, I'm going to store it somewhere for later use. Fine? Now, think about what happened to the convex hull. It started as something small, then it got bigger, then it got bigger, then it got even bigger, and then it got even bigger, and so on, right? Each time, maybe at a different place, you removed some part and added a new piece, right? And remember, each of the parts that I removed, I've still kept it somewhere safe, okay? So now, simply think of reversing all the steps. if you were to reverse all the steps, what will happen? This was the last guy that I added. When I remove this, I'm gonna be left with that. Then I'll remove that part, and I'll be left with that, and so on and so forth. So the coming at it from the other end is equivalent to building all this and removing pieces one at a time. Is that clear? Okay.
And that, can that be done in all one time, because you've already stored it somewhere?
Again, there are two different ways to look at it. If you implement it as a linked list, then you can do it in O of one time. If you store it as an array or pieces of an array, then it'll take a little bit longer. But as he pointed out, it's if you do something called an amortized cost, it turns out that it's not that expensive. Okay. Yeah, it's possible that you need a combination of a linked list and an array in order to make sure that the time complexity is small. But yeah, let's not go into those details for now. I want you to understand this at a conceptual level, because this was nobody solved it in the competition.
Oh.
Which is shocking.
Wow.
Because I don't think this is, if you've done enough geometry problems, this is not the hardest problem over there.
I think there was 140 teams.
Yeah.
And nobody.
No, one person tried, and they did not solve it.
Yeah, they didn't solve it.
Yeah.
I have a hard time understanding the problem itself from reading and conceptualizing it from a word problem to.
But if you
this.
sit with it for 10 minutes, I'm sure you'll grab all that.
Yeah.
And then there's a lot of staring that you have to do.
Yeah.
Okay, this is what they really meant. All right, now I'm understanding it. And to kind of get to a point where you understand the challenges of the problem takes time. No denying that. Yes.
The part about like peeling back
Yeah.
the
Right.
convex hull.
Yeah.
You start off building it,
Yeah.
and then when you go and do the
Correct.
C part, you
Peel
peel
off
off
parts of the
to
ore.
keep the costs low.
Yeah.
Okay.
Exactly.
That's so smart.
Ingenious. That's so ingenious.
I didn't invent any of this. All of this has
I was
been
gonna say,
done before.
the biggest conceptual jump was realizing that you had to look at the convex holes. That
Yeah.
still doesn't seem intuitive.
That is not intuitive, I agree.
Yeah.
But the reason it's not out of reach is because you need to be able to see the x-axis.
Mhm.
Now you have to ask the question, what prevents you from seeing the x-axis? If there's a sliver of the x-axis that you can see, then in here you cannot have any points. Because if there were, then you can't be guaranteed to see the x-axis. That's the key.
Yeah, but the question I have is, initially when you first started going over this,
Yeah.
we always talk in geometry about the simple cases,
Yeah.
right?
Right.
There was a big jump from those cases to now looking at the convex holes.
But the thing is that the simple cases were needed in order to build the intuition. In fact, we had them here, right? So the simple cases were here. These were the simple cases, right? No obstruction whatsoever. Then we said, here's this also is simple because nobody's obstructing,
Yeah.
right? Then we said, this is where the difficulties start.
Mhm.
Now, if you think about this, what will happen here? What will happen is that this point will become part of the left convex hull. Okay? So we know it's going to go to the left, and so therefore I have to bypass it and come here. And this you guys realized it anyways. Okay? So it's, instead of thinking about it as I have to bypass this point and that point and that point, what we're saying is I have to bypass all these points and stay to the right of it. There is no other alternative really for you. Because this guy here is going to go somewhere to the left of the line segment for our point. And so therefore, we have to bypass a whole bunch of points, and therefore it has to be a convex hull. That's it. Once you do enough geometry problems, that'll become clear to you.
But the other question is, can we just look at the triangles we had before and say if we can still see the line segment with all these triangles?
But I'm
this
saying
is,
that that'll come automatically in this.
I'm saying, like, could we do that?
You could, but
Even
the
if it's
thing is that
inefficient.
what we convinced ourselves is that that's not enough,
That's it.
right?
Yeah.
And this is where the problem is. So for instance, when we were looking at these impossible cases, right?
Mhm.
If I only look at this triangle, I say, oh yeah, I can still see the x-axis. If I only look at this triangle, I still say, yeah, I can see it. So each one by itself is not bothering me, I'm gonna be fine.
Mhm.
But it's the combination of the things that mess you up. And here what'll happen, this point will be part of the left convex hull, that point will be part of the right convex hull, and together, they're gonna make sure I cannot see the x-axis. And that is unclear with just simple cases. So for me, this is the simplest impossible case that convinced me that I'm gonna need convex hulls.
I see.
There is no other way to do it, at least not that I know of.
Is the idea of a convex hull, like you creating a data structure that's needed
No.
for the problem?
The convex hull is simply saying, I have to take care of all these points, so therefore it's enough for me to take care of them as one unit. And so I'm gonna just build a convex hull and think of this as a concrete block that's obstructing my view. And that's, once you think about that, you're done.
Okay.
Right? So over here, this point is way more than just a point from which I have to draw a line. It's actually creating an obstacle that will obstruct anything, obstruct something or the other, okay? For sure, I have to draw a line from here to there, and eventually that's gonna obstruct. So I have to cross this point, not just somewhere in between. That's not gonna do it for me. The other important thing to understand here is that the convex hull did not include the segments. And I don't know, this requires a little more thinking to convince yourself. Anyways, I'm not gonna go there.
But they're not relevant. The segments.
Well, eventually I have to connect the points to the line segment, so why am I not including them? So yeah, you have to worry about this a little bit, but it turns out that if I can include the point, I don't need to worry about the line segment. That comes automatically because the line segments are sorted along the x-axis. You gonna say something?
Yeah, I don't know, I realized I was going to so much today, or.
Sorry?
Cause I have like my thing, but I haven't even tested it out, so I don't even know if it's gonna work, and honestly, I'm not even confident, 'cause it's like, I feel like I created a nice test case that's making things really difficult. It may not work for that, but I think it's possible I can go over that, maybe, yeah.
We can, what time is it?
It's 45.
45 already?
Yeah.
Okay, we can spend a few minutes looking at your solution.
This is what I
Are you
thought.
guys okay with this?
Mhm.
Yeah.
Sure.
So what I did is I put like, okay, so I'm assuming it's coming in and like, let's say,
Tell me in English, that's fine, I can
You have to do it
imagine.
on the, you have to do it on the.
No, tell me, let me draw the picture.
What pretty much is I'm gonna look at all the points, right? So first, but here, I also found an issue, so it's like, I don't know. The first
Doesn't matter,
point-
let's look at the core of your idea and see where the problem lies.
So I grabbed the first point, right? Point number one, and then I'm gonna go see where
Where the
the
line
X-
segment is.
where the X is at that point. Then I'm gonna grab the X of point number two, and I'm gonna see, okay, so is point number one less than point number two?
Okay.
If it is, well, okay, but if it's not, and this is where the thing goes into second if statement.
See, looking at the X is not enough. Let me just dispute you there because in your thinking, that needs to factor in. Here you're saying, here's point number one, and here's point number two, okay? And you're saying that because two is to the right of one, it's never going to be a problem.
No,
And
not that it's never gonna be a problem, then there's second case. So that's where I go saying, okay, so if it's, I'm
Can
gonna go.
can I finish my thought, please? So, even though this looks like it's not a problem, I could move two up there. Okay, and it can become a problem. Does that make sense?
Yeah.
No, what do you mean?
Here's my x-axis. Here's number 1. Right? Here's 2 is to the right of it, but now I'm gonna put it over here. Okay? Now I have one needs to connect here, 2 needs to connect here. Do you think it'll happen? Well,
Yeah.
my picture is not so great, but
But that's only if one is beyond 2. If one is beyond 2, then that's.
what do you mean, one is?
Beyond-
You just said that x-axis is great for me to think, right?
No, it's great. I mean, I'm just ignoring that part right now. Like, I'm ignoring the else. I'm just doing the if.
Okay,
So if that's the case, and then I put if I get the x-axis of that wait, then I'm gonna go. Okay, then I'm gonna get that number of get the x-axis of the point where it's at, and then the x-axis of the other point, subtract the difference, and then I'm gonna go use that.
my example tries to tell you that focusing on the x-axis is not enough. That's what my example just showed you. Did you
Yeah,
did you
I
understand
agree.
that? Yeah,
But-
alright. But then you are going to add extra conditions? Because you're just assuming that if it's, so let's say I've sorted, you know that the line segments are sorted along on the x-axis. Let's say I also tell you that my points are also, their exact x coordinates are sorted. You think this is gonna always work? Not a chance. Just because their x coordinates are sorted is no guarantee that it's gonna work.
What's the case?
I just showed you.
If the second pink
Yeah.
line segment is underneath 1, 2 won't have a chance to reach it.
But that's a condition.
But like, what are you, he's asking like what you're using to measure that. He thinks
The
you're just
end of the
using.
segment.
So
in
you're
comparison
checking.
to the point.
Alright, here's your example. This is my x-axis. This is my 1, this is my 2. Now, my points, 1 is here.
But that's past 2. That's past the
Alright,
segment 2.
Where else did you want,
No, but that's the condition that's gonna break, that's that's the case, it's gonna go to the second condition.
no, but I have number 2 that's to the right of it. That was you said the x coordinates of the points, and that's all I'm trying to help you build more intuition to this problem.
Yes, but the problem is, I said that I made it more complicated, that's just a test to see, cause if it's to the right, then
Uh-huh.
you need a test to see is x point 1, is the segment of point 1,
Yeah.
well, is point 1 located where point, the end,
Right endpoint.
where the segment finishes for point 2?
Okay, I think I can even fix that, alright, so I'm gonna move 1, 2,
Cause if it's past point 2.
hold on, give me a chance. Okay, that's 1.
No, I mean, you put it, well, then that would work,
Sorry,
that would work.
you're sure? How do I make this not work? Well, I just have to put 2 somewhere there.
But then the condition that I put inside this if would work for that.
Okay, and what's the condition inside it?
This is where I think I might have a small flaw,
Okay,
because,
that's fine.
with this situation I create here. And
Uh-huh.
that situation being, I'm gonna grab the difference between the point where point 1 stands and the point where point 2 stands, and with that difference, I'm gonna say, okay, if that height of point 1 is greater than, n, the difference, plus the height of point 2, then it's not gonna work.
Okay, all right. It's possible, so let me stop here.
Okay.
Think about it and come back with a better formulation.